This is the AP Physics 2008 question 1, electrostatics. In this question we're given a conducting outer rim and a spherical ball of charge on the inside. So in part 1, you have to find the charge on the inner surface, of this conducting ring. Because it's a conducting ring, this center ball of charge will attract the same amount of charge here, but it will be equal and opposite. So that would be negative Q. Because the conducting ring has a net charge of 0, if there's negative Q charge on the inner surface, then there must be a charge here that will balance that charge and make the net charge 0. So that has to be Q, because Q plus negative Q is equal to 0. Because we're trying to make the net charge. Equal to 0. In part 1, we're asked to find the electric field if there was a surface with a radius that's less than A. So we know, according to Gauss's law, that E times A, area is 4 pi r squared for a sphere. EA is equal to Q enclosed over epsilon naught. So E is just Q enclosed over epsilon naught divided by this quantity here. So in this example, we know that the enclosed charge is 0 because it's on the inside of a conductor. So since the numerator is 0, the flux for part 1, the electric field for part 1 is 0. For part 2, the radius is now between here. So now we can just treat this like a point charge because it's enclosing all of that charge. So the electric field is simply KQ over R squared. Now in part 3 the radius is here, we can see that because there is a negative Q charge on the inner surface, the net enclosed charge would therefore be 0, because Q plus negative Q in this surface is 0. So if the numerator is 0, again, then E is 0. In part 4, the surface is now outside of this entire diagram. So that means that we could again treat this like a point charge. In this case, we know that the net charge is, because the outer ring is neutral and the inner sphere has a positive Q charge, the net charge is just Q. So again, the electric field is just KQ over R squared. Now in the next part, we have to draw a graph. So now from 0 to A, we can refer to here. From 0 to A, we already know that the E field would be 0, so it would be a line right on the x-axis. From A to B, we know it's kq over r squared, so it would look something like this, because it's a inverse square relationship. And again, it's 0 again from B to C. And it resumes kq over r squared. So we're kind of from C to R, from C beyond, it would be kq over r squared. So we can kind of look at it as if it was a single graph. We're resuming at this point like this. This is what the graph will look like. Now for the last part, part D, we have to find the speed of the particle at a distance, if it was a distance 10r away from the center of the spheres. So here's the spheres, and there's a particle very far away, somewhere over there. So if it's very far away, then it has potential energy, and that potential energy eventually becomes kinetic energy. So it has a charge E. So its potential energy would be K, Q, the charge of an electron, all over the distance, which is 10r. And we know in the end, it's moving with only kinetic energy. Once it reaches infinity, there will be no more potential at infinity. So it would be 1/2 mv squared. And in this problem, we're given the mass of the electron. So we're going to solve for v. V is the square root of k q e over, multiplied by 2, so that leaves 5r, over 5r and mass of the electron. And we can write this as the square root of k. We can write q as 1 over 4 pi epsilon naught. So that becomes 20 pi epsilon naught r times the mass of the electron.